Sometimes our surfaces might not have explicit parameterizations. We might not be able to write r of uv is equal to some function of u and v times I hat plus some function of u and v times j hat plus some function of u and v times k hat for functions that we can explicitly write down. Sometimes our surfaces might just be written as f of x, y, z is equal to some constant c. So think back to chapter 14. We had implicitly defined surfaces back then. Well, guess what? If we have an implicitly defined surface here, we can still find surface area for it. So the area of the surface f of x, y, z is equal to a constant over a closed and bounded plane region R. So the point here is that R is the shadow of the part of the surface we're thinking about here. R is the shadow in, let's say, the xy plane or something like that. So the surface area is the double integral over R of the magnitude of the gradient f, of this function of three variables here, over the absolute value of f, the gradient f dot p, where p is one of I hat, j hat, k hat. P needs to be normal to our plane region, and we don't want to divide by 0 here. So this might seem complicated, but let's do an example that hopefully will illustrate what's going on here. Find the area of the surface cut from the bottom of the paraboloid x squared plus y squared is equal to, x squared plus y squared minus z is equal to 0 by the plane z is equal to 4. So the first thing that I'm going to do is I'm going to call big F of x, y, z equal to x squared plus y squared minus z is equal to 0. So we have f of x, y, z is equal to c. C is 0 here. The graph of the paraboloid looks like this. So here is our paraboloid, x squared plus y squared minus z is equal to 0. And the idea is that we are cutting here. We're going to cut this off at z is equal to 4. And so the idea here, so we have the area of our implicitly defined surface, x squared plus y squared minus z is equal to 0. F of x, y, z is equal to 0 over a closed and bounded plane region R. Well, so what is our closed and bounded plane region R? We need to think of the shadow down into the xy plane. And so if up here is z is equal to 4, that would be x squared plus y squared minus 4 is equal to 0. That would be x squared plus y squared. If we fill this in, x squared plus y squared is at most 4. Okay, so this is going to be our region R that we are integrating over. What is p here? What is p hat? Well, p hat needs to be a unit vector that's orthogonal to our region here. And so what vector is pointing in the positive z direction? That would be k hat. So let's use this formula here. I think we have everything filled in here. We'll be using p hat is k hat here. So f is x squared plus y squared minus z is equal to 0. The gradient of f is going to equal 2x, comma, 2y, comma, negative 1. We need the magnitude of the gradient. The magnitude of the gradient is square root of 2x quantity squared plus 2y quantity squared plus negative 1 quantity squared. So that's 1 plus 4x squared plus 4y squared. Okay, we also need the gradient dot k hat. The gradient f dot k hat is going to be, well, k hat is just, you know, this component here. So this is -1. The gradient f dot k hat, the absolute value of that is going to be 1. So we are integrating using this formula right here. Surface area is the double integral over R of this expression. So the square root of 1 plus 4x squared plus 4y squared, that's the magnitude of the gradient f. We found that here. 1 is the absolute value of the gradient f dot p. We said that's 1. Okay, and then dA. How are we going to go about evaluating this integral? Well, the region R here is x squared plus y squared is less than or equal to 4. This is a place to use polar coordinates, so let's convert this to polar coordinates. And this is a place where we are going to need to throw in a factor of r here. So the polar coordinates here, theta would be from 0 to 2 pi, r would be from 0 to 2. And so we'd have 1 plus 4 times x squared plus y squared. X squared plus y squared is r squared times r. We are converting from rectangular to polar coordinates here. So we throw in the factor of r. And so this is an integral we can evaluate by substitution. So that u is equal to 1 plus 4r squared. Du would equal 8r dr, or du over 8 would equal r dr. So there's du over 8. So this is the integral. Theta runs from 0 to 2 pi, and u runs from 1 to 1 plus 4 times 2 squared. I think that's going to be 17 here. And so then we would end up with u to the 1/2 times du over 8 d theta. And so the rest of this integral should be pretty easy to evaluate. The theta terms will give us 2 pi here, times 1/8 times u to the 3/2, and divide by 3/2, multiply by 2/3. Plug in from 1 to 17 here. And so eyeballing this, I think we end up with pi over 6 times, plop in 17 here, 17 to the 3/2 minus 1 to the 3/2 is just 1.